hang out with them. She was a member of the Committee on the Status of Minorities in Astronomy for the AAS, and is now also on the NASA Physics of the Cosmos Executive Committee along with me, and we've worked together on some initiatives and expanding participation in NASA astrophysics there too. She is actually in the process of starting a master's in astronomy bridge program at CUNY, which is really exciting. So it looks like that will happen in collaboration with some other institutes in New York. I think that's about all we've got for now. I'm probably missing something, but what she is going to talk to us about is the growth and evolution of massive black holes in dwarf galaxies. This is something that those of us in my group know is something that's of interest of ours from the electromagnetic side. And what she will talk to us about today is trying to understand from the observational side how these black holes grow, and also, I think, a little bit something about what gravitational waves can tell us about them. And so that's it. Thank you.
Thanks, Ryan. Turn it off. Greetings. How is my sound level?
Great.
Lots of thumbs up. Okay. Hello. Thank you for having me. It is great to be here. I'm having a great time. It's my first travel since the before times. And so it's nice to come to a beautiful place with lots of good trees to be here. So thanks for having me. The next 45 minutes of your life will be about seeking black holes, massive black holes in dwarf galaxies. Okay, here we go. Here we are. By the way, my pronouns are she, her, and a bunch of these people are my collaborators, and the green ones are students, and they are awesome. And I'm going to tell you how awesome they are, and maybe I'll convince some of them to apply here for graduate school, because they're all undergraduates. I work at a community college, and so I hang out with a lot of undergraduates. So we'll see. All right, so some context, especially, I know not everyone here loves black holes as much as I do, and your stars and planets and everything else and cosmological things are all awesome. So I will tell you a bit about some background on black holes. So there's a couple main types. Stellar black holes are somewhere between like 1 and maybe 100 solar masses. They form from massive dying stars when they go supernova, and we expect to find them kind of in galaxies, basically wherever stars are. If you have stars, some of them are going to die, you're going to make some black holes. So that's sort of a basic thing that we've pretty much got a good handle on. We've also got a good handle on supermassive black holes, which are somewhere between 1 million and 1 billion times the mass of the sun. They form with question marks. I'll go at that a little bit later, but we do not know how they form. They just happen to be there, and they seem to be there like less than 1 billion years after the Big Bang. And that is one of the biggest mysteries in astrophysics. How do you build a supermassive black hole very fast? And these tend to be located in the centers of massive galaxies. That's at least where they're very easy to find. If they are in other places, we probably don't really know much about that. Oh, what are you knitting? Nice. I always knit during colloquium. So support your local knitters. Awesome. Okay, so you may look at this and be like, there's something missing here. Anything weird about this? What about like the 4 orders of magnitude where there appear to be no black holes? What about intermediate mass black holes? Do they exist? Like they kind of must. How do you just go from 100 to 1 million? That can't possibly be. There has to be some kind of intermediate mass black hole, but like, where are they? How do you find them? How do they form? Where do they go after they form? Like, how do you measure one? Big question marks here. So that's a lot about, that's what motivates me to do what I do. What the heck are intermediate mass black holes, and why don't we find them? So you probably also know that there are some main types of galaxies, many of which have supermassive black holes in them. But what about our dwarf galaxy friend here? Our ellipticals, sure, you bet we got them. Spirals, yep, got some black holes. But like, where's the boundary between a medium-sized-ish spiral galaxy that pretty much always has a supermassive black hole and a dwarf galaxy, which until recently we thought really didn't have black holes? And even now we're like, okay, maybe some do, but like, why? Why Like who decides, or what physics really decides what galaxies get black holes and what don't? Do they have to be a certain mass? Do they have to form a certain way? So that's another thing that I want to answer, is what determines whether a galaxy gets a black hole or not. Okay. So these intermediate mass black holes in dwarf galaxies, I want to know, how do they get there? When do they get there? And are these the seeds to supermassive black holes in massive galaxies? Are they a stepping stone in how you build a supermassive black hole? Do you start with this sort of medium-sized black hole, probably in the very early universe, and build your way up? But the problem is with supermassive black holes that they have erased their formation history. We can't know how they form. We don't know if they form, say, from like a clump of a bunch of little black holes that merge together, or maybe you have something sort of medium sized and there's some gas that gets accreted along with it. Or maybe there's a little black hole and like a whole bunch of gas, or some other thing. We can't know how the black hole formed because we can only see it as it is today. And everything in it has pretty much erased its formation history. Like we can measure its mass and we can measure its spin. And that doesn't tell us a lot about how it formed and what built it. So supermassive black holes, not helpful, even though we want to know how they grow and become. They actually can't tell us. Their secrets are locked inside along with everything else that goes into the black hole, never to come out. Okay, but intermediate mass black holes are a great way to avoid all of that because they're smaller, they haven't grown as much, maybe they haven't grown at all. How can we look in the local universe for smaller black holes to try and answer these questions? So there's two places to look, and one is looking for AGN in dwarf galaxies. So this is RGG 118. There's an AGN in the center. The black hole mass is estimated to be about 50,000 solar masses, so 5 times 10 to the 4. So small, intermediate mass. Even though there's a big error bar on that estimate, like it's going to be intermediate mass. If you go up or down an order of magnitude, it's still pretty much intermediate mass. So, okay, we have a small galaxy with a small black hole. Let's try and find a whole bunch of these and get a census and figure out if we can learn about what the black holes in dwarf galaxies are like. Another place that might be helpful to look, which we'll talk about more at the end of the talk, is these off-nuclear halo sources. This is a famous one called HLX1. It means hyperluminous X-ray 1, because it's hyperluminous. It's in this disk, like edge-on disk galaxy, but it's in the halo. And the redshift's been measured, it's confirmed it's not like a background quasar or a foreground object. It's this bright X-ray source in the halo. And it's consistent with an intermediate mass black hole based on its X-ray spectrum and the broad line of the H alpha and a whole bunch of other possible measurements. It's consistent with an intermediate mass black hole. Again, plus or minus an order of magnitude in its mass, but intermediate regardless. So what's going on there? It's postulated that in this point source, there is a stellar population, maybe a dwarf galaxy, maybe a star cluster that's merging with this larger galaxy. And some perturbation from the host stellar population has caused the black hole to accrete and to light up. And it lights up periodically. There's probably something orbiting it that's been accreting from every year or so. So if this is a dwarf galaxy like this one that's being eaten by a galaxy like this one, we can maybe look at these off-nuclear X-ray sources and find intermediate mass black holes as well. So those are some cool ideas for places to look. So how do we look? I actually don't look. I do not use telescopes. I use cosmological simulation instead. And so my tool of choice is a code called Changa, which is an SPH N-body code. And I have a few different sets of simulations that I'm going to talk about. The first is known as the marvelous dwarfs, which are 4 simulations of dwarf galaxies that are named after 4 female Marvel superheroes: Electra, Captain Marvel, Rogue, and Storm. And so what these simulations are basically a cube of universe that only has dwarf galaxies. There are no massive galaxies. It's just some volumes of space. There's a whole bunch of dwarfs. So we call them the marvelous dwarfs. Here's a picture. This is Storm Galaxy number 2. right there. So if you see labels like storm 2, that's which simulation they come from. So we have a whole bunch of dwarf galaxies in these simulations. Some of them have black holes. The other set of simulations are known as the DC Justice League, which are named after 4 female Supreme Court justices, Sandra, Ruth, Sonia, and Elena. And so these are different from the marvelous dwarfs in that they, besides being from DC instead of Marvel, they have a large Milky Way galaxy in them as well. So there's one big massive disk galaxy, but then there's a whole bunch of dwarf satellites all over the place as well. And some of those dwarfs have massive black holes. The Milky Way galaxy also has a supermassive black hole. So these are called DC Justice League and marvelous dwarfs. So those are the sets of simulations that I'm going to talk about. And I want to describe a little bit how all of the black hole stuff works before I go on. And so we make black holes in the simulations based on something called the direct collapse model. So how does this work? How do you form a massive black hole in the early universe? Again, like I said before, no one knows, but this is a theory that people like a lot. So if you assume that you have a 10 to the 4-ish Kelvin cloud of gas with a very rapid inflow with a high accretion rate, and it has a low fraction of heavy elements or low metallicity, so it prevents fragmentation, and also a low angular momentum, so it isn't spinning, and possibly an ionizing radiation background preventing the formation of molecular hydrogen. So again, only atomic hydrogen is the only way that this cloud is allowed to cool. It cools very inefficiently, so it doesn't fragment. There's no molecular hydrogen cooling, there's no metal cooling. You just have this big cloud that kind of slowly collapses and eventually can directly collapse into a black hole. Here are some references if you want to learn about the wizardry of this phenomenon in more detail. The thought is that you get something maybe 10 to the 4 to 10 to the 6 solar masses in mass. This will be a rare event, a very special event, but this is the model that we're using in the simulation. So we choose low metallicity gas that's collapsing with a low molecular hydrogen fraction to create black holes in the early universe. And they form at a mass of 50,000 solar masses. Like what I said, dense collapsing, low metallicity, low H2 gas. All right. The other super important thing about our simulations is that they have a prescription for dynamical friction included. The dynamical friction of the black holes. So a black hole we normally see at the center of a galaxy. But what if there's a galaxy merger? The black hole should probably, move around. The gravitational potential is going to change. Your black hole should go along with it. But in a simulation, you can't resolve all of the intricacies of a galaxy. And so you need something that's going to help keep the black hole in place without actually gluing it in place. So we do not fix the black hole to the center of the galaxy. We want the black hole to be able to evolve dynamically. But also, if a black hole gets flung out of the galaxy, we want it to be able to orbit its way back in again. And that's what's going on here. So a black hole gets tossed into a galaxy and it orbits its way back in. And without dynamical friction, there's all these different lines for different situations. But here's the Chandrasekhar dynamical friction timescale. And the resolution of a cosmological simulation isn't good enough for the black hole to reach the center of the galaxy in the proper amount of time. If you add a subgrid model of dynamical friction, then it can. So here's again our model, and for all reasonable model simulations, we get to the proper center of the galaxy in the right amount of time. And so black holes in the simulation are allowed to move around, but if nothing is going on with them, they're going to stay in the center of the galaxy. But if there's a merger, they're allowed to move around and then orbit their way back into the center of the galaxy. So that's going to be important later. I want you to remember that this is something that we specifically model very well. So I've got a little movie here to show you an example of what I'm talking about. This is Sandra, by the way. So Sandra starts out dark, but then gets bright. So the white bits are stars and the colors are gas temperature. Red is hot, green is warm, and blue is cold. So you can see in the center, there is a massive galaxy forming. This will be our Milky Way type galaxy, redshift 0. But there's a whole environment around here with dwarf galaxies. So some of these have supermassive black holes in them, or intermediate mass black holes. There's a supermassive black hole in the middle. You can see there's mergers going on. And so these dwarfs are something I study, but also you'll see that there's these mergers happening. If these dwarfs have their own massive black holes, as they merge with the massive galaxy, they can actually deposit their black holes in the massive galaxy as well. Let me rewind a little bit. I rewind? No, that's forward. That's not what I wanted. I wanted to be like there. Okay. So there we go. So we've got some cool mergers going on. You can imagine that there's some intermediate mass black holes that might get, as the galaxy gets shredded apart, might get left in the galaxy halo. So I want you to remember that. Some of them are going to merge with the supermassive black hole. I want you to remember that. And then some of them just hang out in these dwarf galaxies. Remember that too. Remember everything. That makes sense, right? Just remember everything. I'll remind you of the things that I'm asking you to remember as we go. Okay. Any questions so far? Do you guys ask questions in the middle, or is it not a thing you do?
It's up to you.
Okay. Hey, well, you got a question?
So I'm guessing the temperature gradient, the color map here is where it's high temperature.
Mhm.
What's causing these sort of blue swirls around the dwarf galaxies as they move around?
Aha. Great question. So these blue swirls are the cold gas that's in the dwarf galaxies. So the dwarf galaxies have a lot of cold gas. That's usually star forming gas. A lot of dwarf galaxies are bursty and star forming. So they have a bunch of cold gas in them. And the reason they've got these like jellyfishy tails is because they're under the influence of their larger galaxy. And so once the gas hits like the hot gas of the halo, it's going to start getting stripped off and make these sort of stringy things. There is a bunch of cold gas in the main galaxy too, but it's hard to see because there's a lot of stars kind of blocking it. Any other questions? All right, I don't mind being like asked in the middle if you want to do that. That's totally okay. But you also don't have to do that. All right, let's go on. Okay, so here's a history of how the seed black holes form in the simulation. Here's just a histogram, and the time is on the x-axis, or if you like redshift better, it's at the top. So you can see that there's a burst of black holes that form in the pretty early universe, and after about 500 million years, they stop, except for there's one more that forms after 1 billion years. That's an Electra. She formed one late, she's a late bloomer. So for the most part, this happens super early on in the beginning of the universe, and then it stops, and that's because of this requirement of low metallicity gas. And so eventually, there's a bunch of supernova that go off and then spreads metals and pollutes the whole universe with metals, and then we can't make any more black holes, which is fine because we don't have any evidence for intermediate mass black holes forming in the local universe, which doesn't mean it doesn't happen, but we have no evidence for it. So take it as you will. We think it's a high redshift phenomenon, at least with this direct collapse theory. And this is a histogram of the galaxy mass at the time the black holes form. This is a log scale of the halo mass. So not the stellar mass, but the total like dark matter plus stars plus gas mass. And all of the different shades of purple are all the different simulations, but the total histogram shows the whole thing. And the overall mass range is about 10 to the 8 to 10 to the 9 solar masses in halo mass, which is tiny. These galaxies are super tiny when they form these black holes. But this mass is also consistent with direct collapse black hole halo mass prediction. This is exactly where they're supposed to be forming. And so in terms of that physics, we've got it right. But this is important to note because the black holes have to be able to form in little galaxies if you're going to simulate black holes in dwarf galaxies, in little galaxies. You can't, if you're doing a simulation, you can't have like a mass limit of where you decide your black hole goes, because then you're not going to make any dwarfs. And we know there are black holes in dwarfs in the universe, so you have to be able to form them this way. So it happens. They're very small, tiny baby galaxies with big black holes. When you come to redshift 0, here is our two figures of the occupation fraction, or what percent of dwarf galaxies host black holes. I've got it in terms of halo mass or stellar mass, depending on what kind of thing you're into. But they have the same sort of trend, whereas really small galaxies are not super likely to host massive black holes. But as you get bigger and bigger, like LMC sized over here, we only have a couple galaxies in that bin, so the error bar is large, but it's got like an 80%-ish chance of hosting a black hole. So I would like to suggest that there could very well be an intermediate mass black hole in the LMC, but the LMC is a huge mess, and so finding it is probably going to be very difficult. But I'll bet it's there, statistically speaking. But I'm not going to actually literally bet on that, so I don't really know. Just statistically speaking. So as we get to more and more massive galaxies, it becomes more likely that they will host a massive black hole. So here are some simulated images of simulated galaxies. These are, I think, SDSS GRI images, something like that. Each galaxy is shown twice, so it's face on and then it's edge on. So this is one galaxy, that's one. This is one, this is one, this is one. I don't know if you can see, especially from the back, but there's a red cross that denotes where the black hole is. Does anyone notice anything odd? Yeah.
One's outside the galaxy.
One is outside the galaxy. Indeed. This one is like not in the galaxy, and the others aren't all centered either. This one is nicely centered, but the rest of them are all kind of off. So what the heck is up with that? How do you get off-center black holes in dwarf galaxies? Dun, dun, dun. Turns out that this is actually seen in observations. So this is a study by Amy Rines, who used, I forget where these images are from, but she used she used VLA to find compact radio sources in dwarf galaxies. And again, there is a red cross denoting where the black hole or candidate black hole is. And about half of these are also off center. So there's one, that one's crooked. These guys are all central. So like that one's a little off. That one is in the, like in between two things. Yep.
These are observed, right?
These are observed. The sizes have not been estimated because all there are right now is a radio signal, a compact radio signal. They do not have optical counterparts.
Right.
So we don't know what the size is. They have been determined to not be like background quasars and that kind of thing, but they do require more follow-up for us to get at this. Yeah. So these are candidates black holes in dwarf galaxies based on the compact radio source, but about half of them are off center, and about half is actually what I get in my simulations too. So this histogram shows the distance from the halo center of the black holes in the dwarf galaxies in kiloparsecs here. And you'll see that there's a big peak here. So about half of them are at about 0 or central, but then the other half-ish are off center, up to 7 kiloparsecs or so away, but usually just a couple kiloparsecs. And I want you to remember here, remember the thing I want you to remember, we model dynamical friction. And so this is not a numerical effect. This is not just like simulation resolution being a problem and black hole particles get scattered out of the galaxy. Okay, that's not something that happens in our simulation. And even if it did happen, the black hole wouldn't wander right back in with that sort of an instance. So this is a real, true phenomenon of black holes being off center in a dwarf galaxy. And because it's a simulation, the cool thing we can do is rewind and be like, well, how did they get off center? What is going on here? So it turns out that black holes form centrally. They form in the center of their galaxies, except in I think one case. And they get displaced by galaxy mergers and do not return. So the off-center galaxies are displayed here, each in a different panel of the off-center black holes. And you can see that they all, the distance from the center versus time, they all start out kind of at 0. So they start in the center. And each time there's a star is where there's a galaxy merger. At least it's where there's a galaxy merger that was easily identifiable by looking at simulation snapshots. And like, for example, this one, there were almost no snapshots in the beginning. And so it wasn't clear if there was a merger here or not. I couldn't prove it, but I'll bet there was, but I can't prove it, so I don't know. So for example, this one stays in the center for a long time, and then there's a merger, and then it gets all wacky. This one has a merger, and then it comes back, and then it has another merger, and then it starts to get wacky. This one too. So for a lot of times, a merger is what makes a black hole not be at the center of its galaxy. Ryan.
I'm just curious about those two groups of storm QA when the merger comes and boom, it's very far away from the center.
Mm-hmm.
Is that actually because the black hole has moved relative to its nascent galaxy, or is that because you now have a system where with multiple galaxies merging until you redefine where the center is.
The second one.
Okay.
So to restate that, once the galaxy merger happens, the new remnant galaxy is now suddenly much larger, and the position of the black hole relative to the center of the new stellar combobulation is now much further away. I will show you this in a flip book style right here. Let's see, can you see it? I guess it's better on the side screens. But here is a super tiny galaxy at a redshift of 4.8. And I've highlighted the black hole with a little white circle around it so you can see it. The rest, those little white blobs here are stars. It is a very unexciting tiny galaxy. As I explained before, these are very small galaxies. And so here's redshift 4, it looks kind of the same, 3.8, 3.1. Here, it's hard to see, but there's a little fuzz here. There's a friend coming, a new galaxy is coming. Now the galaxy has sort of flown by and it's up here, but it's actually much larger than the one that has this black hole in it. Here we go. So now you can see this galaxy is of much larger size than this one, which now you can't even see anymore because the black hole that I put in there with PowerPoint has covered it. There is still a tiny fuzz of stars there. And eventually they come together and they merge. And what you end up getting is a situation like this. And so the original host galaxy of our black hole has basically been tidally disrupted and destroyed and accreted by this larger galaxy. And now this black hole is, when you measure its central, the distance from the center, it's much further because it now has this new host galaxy, as opposed to its former host no longer exists. So when I say mergers, I actually mean this specific and weird situation where galaxies that form black holes end up being accreted onto what is usually a much larger galaxy. And then the black hole will end up wandering around for the rest of the age of the universe. Why doesn't it go to the center? Well, a couple of reasons. It doesn't go to the center, one, because a lot of dwarf galaxies are very messy and don't really have a center, or they have core density profiles and so don't have a deep potential well. And so if you have a galaxy without a deep potential well and it's got sort of a flat density profile, the black hole is going to end up kind of sloshing around within that core, but it's not going to, there's nothing for it to gravitate to in terms of a deep potential well, unlike a massive galaxy. Yeah.
What's the ratio of the mass of the black hole to the mass of the galaxy?
The ratio of the mass of the black hole to the mass of the galaxy is somewhere between 100 and 1,000, depending on which one you're talking about. So they're actually overmassive on average compared to like the black hole stellar mass relation.
So the black hole is heavier than the rest of the galaxy by a factor of 1,000?
No, sorry, it's definitely smaller, but the standard ratio would be something like 1 to 1,000 or so for like black hole mass over stellar mass. But some of these are more like 100 instead of 1,000. So they're, yeah, but the stars are always more massive. Yes.
This is still a dwarf galaxy. And
Yes.
do they not always have black holes in the center? I'm sorry, I'm off on my missed that.
For you mean this bigger one?
The new one,
Right. For the most part, they don't. And this is due to a requirement we have about black hole forming, where we think that there needs to be ionizing radiation for there to be a black hole that forms. And this is based on some of the direct collapse formation models. And so the very first galaxies that form, which are often in the like highest density peaks, which will be the biggest galaxies, can't form black holes because there's no source of this ionizing radiation. So you need stars to form first to cause some ionizing radiation. And then in your galaxy next door, the ionizing radiation will heat the gas enough to cause the black hole to be able to form. And that's one of the, it doesn't mean it's true or always happens, but that's one of the main theories about how these direct collapse black holes can form. So as a result of that requirement, the biggest dwarfs in the simulation often don't have black holes initially because they are the first places to form stars, and the first places to form stars don't always have black holes.
But that small one had ionizing radiation when it comes to this one.
Yes, this one or some other friend.
Or some-
Yeah. Yeah. All right. Sometimes you can even have more than one black hole in a dwarf galaxy. So here's an example. I think this one is from Sonia, where there's one in the center. So the stellar mass of this galaxy is 10 to the 9. So a dwarf, but like a bigger dwarf. The central supermassive black hole is 10 to the 6, and this little one on the outside is about 5 times 10 to the 4, so the original seed mass that we put in the simulation, and it's 3 kiloparsecs in the center. And so again, this one is going to keep on wandering through time because not just because there's of the shape of the galaxy, but also we've calculated the dynamical friction timescales for these black holes to how long it will take them to reach the center using the Chandrasekhar formula. And in almost all cases, it's longer than a Hubble time. So in these dwarf galaxies, they're just not, the stellar density and dark matter density is just not high enough for there to be a strong dynamical friction force for the orbit to decay and bring the black hole to the center quickly. It will happen eventually, but not nearly as quickly as in, say, a Milky Way galaxy or an elliptical galaxy, which has a much higher stellar density. Right. So let's talk about accretion and detecting these. Can you find them? Turns out that these black holes don't accrete very much. So this histogram is showing what I call the accreted fraction, or basically how much of the mass of these black holes is from accreted gas versus how much is from like their seed mass or what they started with. So it's the fraction of accreted gas mass to the total mass. So a 0 would be it accretes no gas, and a 1, which is not even on the scale, would be it only accretes gas and gets no mass from any other place. And you can see this giant peak at 0, and it goes out to like 13% or so. But for the most part, these black holes don't accrete very much gas at all. For the off-center black holes, that makes a lot of sense. They're wandering around in a very diffuse medium. They're not going to do a lot of accreting. But even the central ones don't accrete very much, which in a way is kind of cool, even though it's annoying for trying to observe them. But it's kind of cool because it means it gives us a clue to the original seed masses of these black holes. If we can measure the masses of black holes in local dwarf galaxies, if we know that they don't accrete a lot, we can assume that this was the mass that the black hole formed at, which gives us a clue as to how the black hole formed. If it's direct collapse, like I've talked about here, or there are other mechanisms where the formation mass is different, and so maybe those mechanisms are true instead. And so we can use local black hole measurements in dwarf galaxies to give us a clue as to what's happening in the high redshift universe and how these black holes form. In terms of the luminosities, they are too faint to be observed, at least in these simulations. So what I've got here, the stars are all observations of AGN in dwarfs. So higher redshift ones are from Mesqua, these like blue stars across time. Here's time. Here's redshift. This is a bolometric luminosity. There's some local ones, which are the bigger blue stars. And then all of the little circles are from the simulation. All of the redshift 0 dwarfs, their accretion luminosities are here. They're all very faint and not really matching very well with the observations. The black circles are the brightest point at any time from redshift 6 onwards. So like how, like maybe they're not bright now, but were they bright in the past? No, they weren't bright then either. So they get up to, I don't know, 10 to the 40-ish maybe, but that's still at really high redshifts, and that's bolometric. That's not like X-ray luminosity. So not observable. So black holes in dwarf galaxies in general, at least in these simulations, don't accrete a lot. This is a small data set though. So I'm working with grad student Ray Sharma from Rutgers, and he's been using the Romulus simulation, which is a bigger and better version of what I've been talking about, because it's a 25 megaparsec uniform volume, so there's tons more galaxies. And he actually does find dwarf AGNs. And so the Mesqua data that I was talking about before are these green diamonds, and Birkal's X-ray data are these X's. And if you look at X-ray luminosity versus stellar mass or versus star formation rate, all of these circles are simulated dwarf AGN in the Romulus simulation that match up really well with a lot of these observed points. They're colored by Eddington ratio. So the ones that are yellow are accreting more, the ones that are purple and black are not accreting. And so you wouldn't necessarily see the ones that are accreting they're accreting very low anyway. But so if we measure their X-ray luminosity, these do match observations pretty well. So Ryan, and then back there.
I'm just curious, is there a reason why they only get up to 1% of anything? simulation?
Because they're dwarfs.
So they just never
Yeah,
get beyond that, that's really.
yeah. Yeah, that could be it for this case. Was it Brian back there?
Yeah.
Yeah.
So the runner simulations have a similar sort of physics background, like the formation of black holes.
Yes, it is very similar, except that there isn't molecular hydrogen in Romulus, and so there's a little bit of a difference in terms of that formation mechanism, but the low metallicity and all the rest of it is exactly the same. So it's still based on direct collapse, but it's not exactly the same physics because it's a little bit lower resolution. Okay, so there can be dwarf AGN, but in my small set of super high resolution dwarfs, there weren't any. So we're still looking into like what actually causes and like triggers an AGN in a dwarf. Is it like what triggers an AGN in a massive galaxy or not? Stay tuned. Hopefully Ray will answer that. All right. So something that I wanted to investigate, if you can't use photons to measure an accreting black hole in a dwarf, can you figure it out dynamically? So here in this is about to animate, but this little white dot is the black hole. Is it going to animate? Yeah, okay. So what I did with some RAU students is I cut out one of these dwarfs and I simulated for another 3 billion years. And I wanted to know if this wandering black hole was going to stir up the stars with its gravitational pull dynamically, and if you could measure the dynamics of the stars. That was something I wanted to do. So this galaxy is very little. This is Captain Marvel number 5, by the way. It has a stellar mass of 1.2 times 10 to the 7. Its black hole mass, about 10 to the 5, so about 100 times smaller than the stars. We also did an identical simulation with no black hole and one with an even heavier black hole. We made it 10 to the 6, so giant. So can you tell? So we could tell that the black hole's orbit was decaying. It was actually undergoing dynamical friction and working its way toward the center of the galaxy. After 3 billion years, you could see the black hole's orbit. It gets kind of there. And then the super heavy one that was 1 million solar masses, it does it much quicker. So we feel confident that we had some realistic dynamical friction going on. But if you measure the velocity dispersion of the stars, the black line is the fiducial run, the red one is the heavy black hole, and there's a blue dotted line, which is no black hole. There's no difference. Like, I mean, they change, they're not identical, but you can't differentiate the galaxy with a black hole from the galaxy without a black hole. Even the galaxy with a giant black hole doesn't give you a difference in 3 billion years of evolution. So you can't tell dynamically either if there's a wandering black hole in a dwarf galaxy. So how can you find them? LISA will give us a lot of clues. What the heck is LISA? The Laser Interferometer Space Antenna, giant gravitational wave detector in space. It will, oh shoot, I have to change this date. 2034 is now outdated. It's now 2035 plus some plus n, where n is between 0 and 5. Don't know. Well, stay tuned. But anyway, here, okay, so here's a little animation of like a cartwheeling triangle following the Earth orbiting the sun. That will be LISA. It will cartwheel after the Earth. It's enormous. The separation between its arms is 2.5 million kilometers, which is more than 5 times the Earth-Moon distance. For reference, LIGO is 4 kilometers. 4. Oh. So LIGO is super great. I love LIGO a lot, but I love LISA more than LIGO, because it will be great. So what will it do? It will do many things, including observe merging intermediate mass black holes to high redshift. So that is what this beautiful rainbow plot shows. So this plot has distance on this axis and redshift on this axis. So now is at the bottom and a long time ago is at the top. And the x-axis has the sum of 2 merging black holes. So if you add them together, that's whatever you get. The colors are the signal to noise that LISA will see from the merger. And so obviously things that are close by will be very loud for LISA, and things that are farther away will not be as significant. But you can see that the signal to noise at a redshift of 20 is still like a few hundred for black holes in the intermediate mass range. It's amazing. You can't, there's no photons at redshift 20. Like, lasers aren't, they're trapped by stuff. The gravitational waves don't care about the stuff. They'll just go through it. And so we can get a cool window into this earliest part of the universe on gravitational waves from LISA. Even if there are no photons, we will know if black holes are merging, we will know how often they are merging, and we will know the masses that they are merging at. It's amazing. It's so amazing. So, do black holes merge in the simulations that I've been talking about? They do. They even merge in dwarf galaxies. This is only including the dwarf galaxies and not the more massive ones. So each black dot that I've added here is a black hole merger that happens in a dwarf galaxy in these simulations. And the numbers here are the mass ratio. So like a 1-to-1 is equal masses, 1-to-3, one of them is 3 times bigger than the other one. There's a couple here that are buggy and you should ignore them. So the 1-to-112, don't think about that. That's not a thing. The mass ratio anyway isn't right. So most of these mergers happen between redshifts of 0 and 12. And their mass ratio is mostly between like 0.2 and 1, which is pretty cool. So LISA can definitely detect these kinds of things. But something that I want to make you aware of is that in these cosmological simulations, we don't actually resolve all of the stages of black hole mergers. So our spatial resolution is maybe a few tens of parsecs. And if you study black hole mergers, you know that there's this thing called the final parsec problem, and that when black holes get close together, they have to figure out how to get close together, and they have to make gravitational waves and do all this stuff. In the simulations, what we do is go, oh, they're close together, and they're now whooshing by, bing, now they've merged, which is super wrong, but there's not, we're limited into what we can do here. However, my RE student, Victoria de Kuhn, has used an analytic delay time calculation for the mergers that happen in these dwarfs to include effects from unresolved dynamical friction and gravitational wave hardening to see, will they actually merge, or are the simulations just grouping things together that will actually take a gazillion years to merge? And so of the colored stars that she was able to make this measurement for, 4 of them will merge within a Hubble time in between 100 million and 1 billion years. 1 of them will merge in 30 billion years. And so that one definitely not observable by LISA unless we have a new LISA 30 billion years from now, which can take our measurements. And then the rest of them were unresolved. And so basically the galaxies were too small and she couldn't measure the stellar properties of the galaxies enough to figure out if they could merge or not. But this is heartening. So we think, okay, even if we can't resolve all of the processes, if we do some extra calculations, it probably won't take too much longer for the black holes to come together. And so hopefully we'll submit this paper in November, and hopefully I can convince her to apply Dartmouth, and then you can hang out with her for the next several years. We'll see. All right. Oh, and she also calculated the strain, the gravitational wave strain that LISA will detect for each of these mergers. And so the strain is basically how much space-time is going to wiggle when the gravitational wave goes by versus the frequency of the wave. So everything that's above this blue line is what LISA will be able to detect. So LISA can detect anything that's on top of the curve. And so as the black holes in spiral, or this part here, it enters the LISA band, we can watch the in spiral. The coalescence is the knee here. And then once they coalesce, it drops down. And these mergers take a while. They take on the order of weeks, as opposed to the LIGO mergers, which happen in like a second. These happen for much longer. And so we'll be able to measure their properties for a longer amount of time. All right, I think this is the last slide. So massive black holes, or massive galaxies also have black hole mergers. So I've been basically completely ignored the massive galaxy in the simulation until now. But it turns out that as dwarf galaxies merge with the massive galaxy, some of their black holes will merge with the supermassive black hole. When that happens, you get a mass ratio of about 1 to 50 or so. So this, if we include all of the black hole mergers in the simulations, including the ones in the massive galaxy, you get this distribution, which has this big peak, which is at about 1 to 50. And then a bunch of, these are all like kind of the dwarf galaxy mergers. And then these are all mergers with the supermassive black hole inside the central Milky Way. And so I want to bring you back to this situation that I told you to remember. So now we'll remember it. Remember that these dwarfs aren't just hanging out in space, but they also build up the halos and the properties of larger galaxies. And so if you have a bunch of dwarfs that are merging with your massive galaxy, and the black hole goes with the supermassive black hole, you'll get this characteristic mass ratio of 1 to 50 or so, which should also be detectable by LISA. However, there's been almost no waveform modeling of this 1 to 50 mass ratio because it's computationally very difficult. And so we have about 15 more years to work hard to do some of that, or else we're not, if these mergers happen, LISA will measure them, and then we won't understand what LISA sees. And then I'll be sad because I'll be like, I've been telling you this since 2021 or before. And they'll be like, all right. So we got to get on it. All right. So in conclusion, intermediate mass black holes in dwarf galaxies are awesome to think about. So dwarf and wandering black holes can give us clues to the original seed mass in the early universe. Many black holes in dwarf galaxies are not central due to dynamical effects. Black holes in dwarfs can be pretty hard to detect, whether they're central or they're wandering, but gravitational waves might be able to help with that if they merge. And very few supermassive black hole mergers in these low mass galaxy environments have a 1-to-1 mass ratio. 1 to 50 is more common. And so we got to tell the LISA modelers to get on that. I tell them that all the time, but now you can help because now you know. All right, that's what I got. Thank you all for your attention.
Any questions already? Yes.
Thank you so much. That was a wonderful talk. I was wondering, would there be any reason to expect for the distance? When you showed that animation of the smaller dwarf galaxy merging into large dwarf galaxy and the black hole hanging out kind of relatively far from the center, is there any reason to expect the dependence on the distance from the new center on the mass ratio of merging dwarf galaxies?
Yes, I would think so, because if they were more comparable in mass, then you would probably have a higher chance of having the black hole penetrate closer to the center of the mass distribution sooner.
Okay.
So I think an equal mass ratio dwarf-dwarf merger would be more likely to end up with the black hole closer to the center than these very unequal mass mergers.
Okay.
Yeah.
What are the differences between each of the main models? Are you visualized differently, or are they all just different runs of the same simulation?
They are not the same simulation. They are all different. So the way that we select them is we have a big uniform volume of universe, and then we say, all right, here's some dwarfs, and here's some dwarfs, and here's some dwarfs, and here's some dwarfs, and we re-simulate them at higher resolution, including more physics. Or like, here's a good Milky Way, here's a good Milky Way, here and here. And so that's how we do it. So we usually try and choose, like if we're choosing, we'll be like, here's a Milky Way with a boring merger history, and here's a Milky Way with an exciting merger history, and here's one with a neighbor like Andromeda or something like that. So we can sort of choose what it's going to end up with by first simulating like a sort of coarser version of the universe and then selecting and refining from there.
Thank you.
Can I make more light by hitting
Sure,
these
sure. The
buttons?
second one is down. Yeah, there you go.
Ah, okay.
So I have a related question to that, actually, if I may take the prerogative, which is, it's computationally expensive to run these things with the black holes in there. And you're trying to find out what happens to the black holes. So you've got a dynamical friction prescription and everything, and you're actually following the black hole part.
Mhm.
If you take all of these, but of course there are bigger cosmological simulations that run lots and lots of galaxies,
Mhm.
but they don't necessarily track the black holes in the same way. And
Right.
what I'm wondering is, does this suite of simulations, is the behavior of the black hole sort of regular enough that you could make some statistical predictions by using a larger galaxy simulation, and then just kind of say, okay, well, based on, the marvelous dwarf simulations, when two galaxies of this mass collide, the black holes are likely to do something like this, and kind of paint it on there rather than actually following the black hole particles. This I'm obviously out of a reason for asking. It's a potential project to work on, but I'm.
Yeah, if you were gonna do something like a semi-analytic model where you are already trying to sort of make broad estimates of what galaxy properties and corresponding black hole properties are gonna be, then yeah, you could probably, I would probably use the Romulus simulation as a better way to get a statistical sense of what's going on, just because it is an actual uniform volume with a, like, that's what it's for. Like, so these ones that I'm talking about, the Marvelous Dwarfs of the DC Justice League, are Zoom simulations, which are basically, here's my favorite piece of universe, I'm gonna look at it really hard. But that's not statistically valid to do. You can't just do that. So I would say use Romulus, but yes, you could probably use that as a basis if you were gonna try and do what you're talking about. There was a question.
Yeah, just a few slides back. This one.
Mhm.
This is, this bottom axis was the combined masses of two merging galaxies.
Yes, black holes.
Sorry, black holes.
Yes, and it does assume a mass ratio of, I want to say 1 to 4. It does have an assumed mass ratio, but if you change the mass ratio, the curves shift a little bit, but it's mostly the same.
What I was confused about with this graph is that the signal, the noise gets worse with more mass.
Yes,
How come?
because at that point, the waveforms become too large, the wavelengths become larger than the LISA detector, basically.
So
And so, yeah, then you just need a bigger LISA.
like it's optimized for certain scales.
Exactly. So the 2.5 million kilometer arm length gives you a basic scale for the type of size of the gravitational wave that you can measure. Just like a
I
telescope.
guess that makes sense. Yeah, okay.
Yep.
It's larger than the wavelength. It's not
Yeah.
like this. All right, cool. Thanks.
Just a quick comparison, where would LIGO kind of sit on this plot?
Here.
Just a tiny, yeah. okay.
Yep, it's here. So it's on this. So yeah, LISA can't do this, these black hole masses, and LIGO can't go out like LIGO definitely can't do redshift 20. It's much more local, so it would be a little bump right there. There actually are figures that have all of them together. And then if you do want to add pulsar timing arrays, they do this over here. Well, maybe not over here, but like they do this.
Good questions. Awesome. Well, thank you very much.
Thanks, everybody.